In this video, we shall look at electric field produced by a line charge. Assume that we have a line charge, a finite line charge as shown in this figure, and it is centered about the x-axis like that, and the line charge is aligned along the y-axis. So it is of length 2a. So the higher end or the top end is at y equals to a, and the lower end is at y equals to minus a. Assume that it is a positively charged line charge. Here we will address the value of electric field at, say, a point P, which is a distance x from the line charge. We will also address two cases. Case 1, when this entire line charge shrinks into just a point charge at the origin. That means the entire length of that line charge goes to 0, or a goes to 0. Case number 2, what happens when this finite line charge extends all the way to infinity? Namely, this entire length 2a goes to infinity. Now let's do this problem. A positive electric charge, total charge is capital Q, is distributed uniformly along a line with length 2a. That is this line in blue. So the line charge is along the y-axis as shown. Find the electric field at point P on the x-axis, a distance x from the origin. What happens when the line charge shrinks to a point charge, and what happens when the length of the line charge becomes infinity? Let's do the very first part of the problem. Find the electric field at point P. To do that, we need to divide the entire line charge into very small segments, one of which is shown here, like that. Let's assume that this segment is so small that it can be considered as a point charge, and the total amount of charge within this element is dq. Let's also assume that the length of this very small element is dy. Also, the position of this element is y measured from the origin. So that is the coordinate of this element. 0, y. First, we address the electric field created by such element at point P. What is it? The direction of the electric field created by such tiny element at point P is simply given by that arrow, like that, because it's a positive charge. The magnitude of that electric field is given by the familiar looking expression that we have seen before, which is the constant k times the charge dq over that distance squared. R can be calculated from Pythagoras theorem. This is x, that distance is y. So R is just square root of x squared plus y squared. And R squared in the denominator is simply x squared plus y squared. Next, we need to get a little bit clear with this amount of charge dq. Can we express dq in terms of capital Q, which is given in the problem? Since we are told that the charge is distributed uniformly along that line, the charge density must be constant. What that means is amount of charge per unit length is a constant. Thus, dq, which is the charge contained within the length dy, must be the same as q, which is the charge contained within that entire length of that line charge 2a, which indicates dq is just q over 2a times dy, and this can be put in there, and we get this expression. Note that this is the expression for electric field along this line or along that direction. If you take the unit vector along the direction to be r hat, then the vector dE is just all this expression times r hat. The vector dE must have components, x component and y component. The x component will go that way, so that is dEx, and the y component will go downward, and that is dEy. So let's write these two components down. dEx is dE times cosine of that angle, let's call it theta, and cosine of theta is just x over r. So x over r is square root x squared plus y squared. Substituting the expression for dE, we get kq over 2a x dy over x squared plus y squared to the power 3 over 2, because this has a power of half, this is power of 1, so you get 3 over 2 upon multiplication. So let's write that result here. Now let's do the y component. So the y component of dE is dE times sine of that theta. Sine of that theta is y over r. So y over r is square root x squared plus y squared. Multiplying by this dE, you get kq over 2a y dy over x squared plus y squared to the power 3 over 2. And we have written the resulting expression there. Now let's sum up the contribution throughout the line charge. So there are many such contributions, and we should move all the way from down all the way up to cover the entire line charge. So that means we are determining the complete x component of the electric field. And mathematically that means it's an integral of dEx. Substituting the expression for dEx there, taking out all the constants, you get kq over 2a x dy over x squared plus y squared 3 over 2 integral. You see that x has been taken out of the integral. That is because as you move from down to up or up to down, the x does not change. X represents the position of that observation point. So x is a constant as far as this integral is concerned. This integral can be evaluated using standard integral table. Let's write down the constants. From standard integral table, that integral is just 1 over x squared y over square root x squared plus y squared, and of course we need to substitute the limits, minus a to a. You see that this x will cancel one x from below, and you get kq over 2ax. Upon substituting the limit, you get 2a over square root x squared plus a squared. And this 2a will cancel that 2a to give you the following expression for the x component of the electric field. It is kq over x times square root x squared plus a squared. And let's write the expression there. Now let's do the y component. The y component can be evaluated similarly by integrating dEy, which will give you, taking out all the constants, kq over 2a integral of y dy over x squared plus y squared to the power 3 over 2 from minus a to a. Again, from standard table, you have that integral for e sub y worked out to be minus 1 over square root x squared plus y squared, substituting the limits minus a to a. And you see, once you have substituted the lower and upper limit, this will give you identically 0. So there is no y component to the electric field. There we have it. The full electric field in vector language is given by just that. This is the unit vector along the x-axis. Now let's see what happens when the line charge shrinks to a point charge. Now that means when you let a to 0 in this result, you see that the electric field will simply go to kq over x squared, because now x is much larger than a, and a can be ignored. Of course, let's not forget the I hat. And as you can see, this is just an expression for electric field of a point charge. So what happened here is that under the limit, when a goes to 0, the line charge has shrunk to a point charge. Next, let's see what happens when the line charge becomes of infinite length. That means a goes to infinity. When a is much larger than x, then the electric field will simply become kq over x times a, I hat. So this is when a goes to infinity. So what happens here? The field magnitude depends only on the distance of that point P from that line charge, namely that distance is x. Another conclusion from this result, if you have an infinite line charge, we can say that at any point P surrounding that line charge, let's say this point or that point and that point or that point, if the distance from that line charge is all, say r, 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 and r, the electric field at those points will be the same, the magnitude of the electric field that is, and it is given simply by that expression that we have found earlier. That in writing this result, it's usual to write in terms of linear charge density, which in this case it's the amount of total charge capital Q over the charge element length. So using this result, we can write that in terms of lambda as quite simply k 2 lambda over r. And that solves the problem. Thank you for watching.